Welcome to a new test and teardown video. This time it's a very simple Hewlett-Packard 461A amplifier. And I think this is probably one of the more simple HP products I got. I think this means it goes to 150 megacycles. Oh, megacycles. But I haven't yet figured out what IK. Oh, now I got it. It's 1 kilocycles. Look at that. I got it. I've been looking at this all day, figuring out what the heck is that, but it's a 1. Okay, 1 kilocycles to 150 megacycles. That's actually quite wide band. How could they make this? And it's the old logo and the old font, and yeah, it's from a company called Stono, and they painted their instruments like this, and also here on the top, probably so it would go back to the yellow storage area, so somebody else can find it in the future. That is nice. And this one uses this a little bit annoying power supply connector, but I of course got that one. I want to open this one first before I do anything else, because you never know what you find. Some sort of leaked or blown up capacitors. Of course I got this. That was a little bit of a fight. See, all this orange paint drove me a little bit nuts, and it was really, really dirty and nasty, so I managed to clean it quite nice and fine. And we are now inside. It's a little bit more, yeah, there's a little bit more of everything compared to what I imagined. So it's a 2-layer board, where the top layer is the ground. And yeah, it's of course only transistor based. There's a little power supply here. I believe that one is a Zener diode and a transistor. That is all. Only 2 diodes and a tiny, tiny little transformer. Maybe that one is also a part of the power supply. Okay, so there's a little pre-regulator. This is probably the feedback. And that will be the power regulator, power supply thingy. Yeah, that one is definitely connected to the power supply. Voltage, line voltage range selection right there. And filter. Yeah, that is some funny stuff. Very old capacitor. I think this unit is probably a little bit older than I imagined. It looks like the transistor's been replaced quite a lot of times. Oh, that is nasty. And then they just replace all of them every time they blow this up. Okay. And there's a little loose wire. Where is that one going? So I need to figure out where this little black wire goes. Oh, there's something really cool I want to show you. So this is the switch here at the front, right? And it goes off. Let's go again here. Off, and then 20, and then 40 dB. Okay, so this is what we need to remember. Look at that little, so this is the input BNC connector, and when I move, look at that. This is the 20, and this is 40. So in 20 dB, I activate some sort of an attenuator on the input. That is a little bit funny the way that is made. probably for good wideband performance. So input goes via this coax cable into this. So now I need to remember that is the input, and output is that one. So obviously output is the biggest transistor, and that is the... Ooh, there's also a big one right there. I don't know. Let's just see if this works, but I need to figure out what is the idea. Maybe this is for a voltmeter or something, and then they check it out what is working, and I don't know, because I don't see where this one should go. It's not going anywhere. Let's look a little bit deeper at the power supply. I was able to find a schematic so I can show a little bit of what is going on. So this is the output transistor, the series regulator, and this is the control transistor, and that will be the Zener diode. So let's look at the schematic of the power supply. I think it is very, very funny to see how this is done. I mean, let's just start at the secondary side of the transformer. You see all the capacitors, all 5 capacitors, they are mounted in parallel, and 2 diodes, they half rectify each half side of the wave into a full wave rectifier, creating a negative 25 volt on the top side. Okay, and then it goes to the series regulator Q1, and that is a PNP transistor, and it's regulating in the negative supply voltage. That is so funny. And the positive 15 volts, that is the bottom of the schematic. The lower line is a positive. I really hate it when people do this. I really like if you can have positive at the top and negative at the bottom, but it's just me, probably just me. I'm sorry about that. But anyway, you can see the Zener diode creates about 15 volts offset from the center point they call the chassis and ground, and the only place in the power supply, this is this is the Zener diode there, and of course a 2K7 load resistor for the negative supply. So you need to have some load on the negative, and this also bias the Zener diode. And the fun thing is this control transistor. Try and see the 2 resistors, R4 and R5. They control the base of that transistor to a center point that is very close to 0 volts, and the 0 volts is the emitter of that transistor. So this is how you regulate the output. The output of the series regulator here is pulled on initially by R2 and R3, so this pulls the transistor on, and Q2 is doing the exact opposite, it pulls it off. So I think that is a really funny power supply. But the cool thing is that you can imagine if the load this is designed for uses all its power between the positive and the negative 15 volt, and it's not using any power to or from a chassis, then this is is an okay way to do it, really. So while we are at it, looking at schematics and try to understand the circuit here, this is the amplifier board, and this is the input emitter follower, and that will be the 5 amplifier stages and the output emitter follower. All those inductors right here, and What is that down there? This looks some burned stuff down there, by the way. I'll have to investigate what that is. This can't be good. Well, anyway, what I was trying to say is that all those inductors and all those resistors and stuff, that is the frequency compensation, local feedback for each of the amplifier stages. So you can make a flat gain response. That was just old burn marks under that resistor from a previously replaced resistor. Oh, by the way, now you can see this resistor with a few windings. So that is an inductor handmade over that resistor. And again, that is, of course, frequency and gain compensation. Here is the amplifier schematic, and you can now see all the nice details about the different transistor stages I just shown. I think it is quite interesting to see all the different frequency compensation components, the inductors and capacitors and resistors around each transistor, controlling how much gain you have in each of the transistors. So I will now try and see if I can get this thing up and running. So I just powered up, and look at that. We got light in the lamp, and that will be the negative, very close to negative 15, and the positive should be right there. And that is also very close to 15. So, I mean, I'm not going to go and poke around with the power supply. I also went into AC mode, and I didn't see anything at all. So, yeah, let's try and play with the amplifier. So it looks like the unit is more or less working, but I think I already found a few problems. See? But anyway, this is 40 dB gain. I'll now take the input. You see a little bit of noise here, right? So I will take my input, and I only got 10 millivolts peak input. That is the input. Let's go into my channel here and then dial. See, this is 5 millivolt peak, and you can see we got 2 divisions. So this proves my input is 10 millivolt peak. All right. So now we're going to take this input and stick it into the input. See, that is the background noise of the amplifier, generating quite a lot of noise. We'll crank this all the way up. And here is my signal. I am in 100 millivolts per division. And I got this little measurement here. It says 270 or something like that, millivolts peak. So that means if you divide these two, and you have the, you of course needs to calculate gain in voltage gain. That means I got only 28 dB, and I should have 40. So, I mean, I should have 1 volt peak if this amplifier would have worked. So there's definitely something wrong with this one. Probably one of the stages is fried. But what I want to do is I want to go into the frequency and then just change the frequency to 1 megahertz and see if there's any change. No. And so let's go to 10 kilohertz and see if there's any change. Not a lot. So the good thing is the frequency compensations and all the different things here is more or less all right. So at 10 kilohertz it seems to be working. Okay, let's try 1 kilohertz. And it's still working the same way. Okay, now we're gonna go crazy. Let's go 100 megahertz. Okay, and we got the same. This one is specified to 150. So let's try 150. Oh, see, got a little peak here. This is 180. But it should be flat. Plus minus 1 dB all the way to 150. And then whatever it does outside of the requirement, I mean, that is perfectly fine. And then nothing is left here at 300 megahertz. I think I'll try and repair it using a 10 kilohertz signal, because that means it will be so easy for me just to poke around with my scope probes, and then it's not critical with grounding and probing and how you do this and that. And probably I will find one of the stages not giving me any kind of fantastic gain. At least that is my idea. It didn't take long for this to work. So that will be my 10 millivolts of input. And I got now close to a volt peak here. Ha. And this is at 70 megahertz, by the way. What did I do? Okay, let's try and get some light here and show you guys what I did. So that will be the input emitter follower. That was the original transistor. And it is, of course, the input transistor that takes the most pain when you do something bad, like static charges or whatever you do to it. It's gonna go straight to the first transistor. And so this time I put in a little socket, just like that, right? So now I can easily change the transistor, and it should be good to go again. I also adjusted the frequency compensation a little bit because my transistor got a little bit different performance, and I think somebody else also poked around with this, and I think this is why I needed to do that. And now I have a much more nice and flat frequency response, so that it will be 70 megahertz. La 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 la, you see. Oh man, I'm happy about that. So yeah, I think I will just say that is the end of this video. I'm quite happy about this because now I have a really fast preamplifier for all sorts of experiments with sub millivolts where I need to be able to see something. And scopes, they don't really like those millivolts signals. It's all drowns in noise and all that kind of stuff. So yeah, it sounds like a really, really simple product, but I can really use this for something. So that's a kind of good score.